So here's the code for Lab 8, and the goal of Lab 8 is to drive the robot to the center of a rectangular area. So right here we have our variables initialized. Then we start our loop function. Wait for the button A to be pressed, wait 2 seconds. Then you want to make sure you have the red light turned off. And then once you have the red light turned off, you're going to loop 4 times, and these 4 times you're going to have the robot take a measurement from the ultrasonic sensor of how far away it is from the barrier of the rectangle. Then you're going to turn it 90 degrees and wait half a second. And of course you store all these measurements into variables. So the first measurement is going to be the first width distance. The second measurement is going to be the first height distance. Third measurement is going to be the second width distance. And the fourth measurement is going to be the second height distance. And the total width and total height are self-explanatory. And so right here, we calculate the width to travel in this calculate width to travel function. Which takes in 3 floats, total width, first width, and second width. So if the second width is greater than the first width, then we want to return a width that is the total width, half of the total width minus the first width. And you want to rotate the object backwards 180 degrees. Or if the second width is less than the first width, you want to return half of the total width minus the second width. Go back up here. So wait half a second, then you want to drive straight. This is a function pulled directly from the previous labs. I'll show that later. Wait half a second, and then you want to calculate the height to travel, which has its own respective function. And the height to travel, let's see, takes in a total height, first width, second width, first height, and second height. It takes in a first and second width because when we do these comparisons, we have to keep in mind the original position that our robot was in. So the first and second width and where we're facing relative to them at the beginning of the program is actually important to know for when you want to face the proper height to face to drive towards the center of the rectangle. So if the second width is greater than the first width, then you're going to run through some further if statements. If the second height is greater than the first height, then the return height is going to be half of the total height minus the first height, and you're going to turn 90 degrees. Or if the second height is less than the first height, then you want to return a height of half the height minus the second height, and then turn 270 degrees. Else, if the second width is less than the first width, you're going to do this up here, except the converse of this. Well, almost the converse. You're still going to return, if the second height is greater than the first height, then you're going to return half of the total height minus the first height. But the difference is that you turn 270 degrees, which is a left turn essentially. And then up here you turn left if the second height was less than the first height. But right here, you want to turn to the right, which is just turning the 90 degrees. And I have to turn the robot 270 degrees because there is no left turn parameter I can put in the turn robot function. So here's the drive straight function I had from the previous labs. Nothing really too different here. Just stabilizing the robots and compensating for those differing motor speeds between the left and the right motor. Our get distance with sensor function, this is for the ultrasonic sensor. Turn robot only takes in a degrees to turn, so it can only turn clockwise. It's only programmed to turn clockwise. So that's why I had to do the robot turning 270 degrees to simulate a left turn. And at the end right here, I had to reset the encoder counts for both the left and the right wheels because for whatever reason, when I tried to turn the robot more than twice, it would not do that. So I had to do this. And then our count for distance, which helps us translate a distance to travel in pulses that the robot can read. And that's about it for this. And over here I have a environment marked out. It's like a rectangular boundary. This is roughly 28 inches across, and this was roughly 55 inches across. So this way, say about 14 inches this way, and this way is about 27 and a half to 28 inches. And that's X marks the spot. That's where the robot needs to be, regardless of where it's positioned in this rectangle. Now I use these two suitcases right here, but the robot is gonna act like these two suitcases are just one big solid boundary, but it's inside of like a massive rectangle. So I'm gonna place the robot at a random corner, perpendicular to the wall, like the lab says, and I'm gonna press the A button. Scan the first measurement, scan the second measurement, scan the third measurement, and then the fourth. So the second width was measured to be greater, so it's going to face towards the second width. And then it's going to rotate 270 degrees, simulating that left turn, and it's going to hit X marks the spot. There's a red LED to signal that it's done. And it's pretty darn close to X marks the spot. And I'll put the robot right here this time. So I'm gonna press the A button. First measurement, second measurement. Excuse me, that's the measurement right there. There you go. Very close to the X again. So there's lab 8.